This is Selvakumar Subramanian, and I'm doing my master's in computer science at Georgia Tech University. And today I'm going to present the paper Optimal Control with Safety Red Lines and how Internet of Things can be safely protected via micropolicies. So there are a lot of references has been taken, and the references are mainly taken from the paper submitted by Henry, Robin, Saman from the respective universities, Information of Trust Institute, in University of Illinois, and the Rutgers University. Yeah, let's get deep into the presentation. Yeah. So, why do we need Internet of Things? What benefits it brings in, and what challenges it gives to us? For example, it gives a better communication, better access to the informations. So, and also it enables machine-to-machine communication easily. So this is one of the main advantages of Internet of Things, and it also brings in a lot of automation, and which in turn you can also control the devices centrally. All this happens because of the better communication. For example, when you connect your physical devices to the internet, they be stay connected, and there is a total transparency in how that particular machine is kind of working. It can be monitored globally, and you can also make the alerts, make the system controlled from a central place without in terms of automation. You can even do this without even human intervention. So and also it saves the time. For example, when the machine to machine interaction provides better efficiency, and they provide more accurate results, which can be obtained very fast. So this results in saving some of the valuable time. Instead of repeating the same task every day, this can be automated, and it enables the people to do other creative jobs. So this is one of the main important aspects of Internet of Things, and it also brings in a better monitoring, which is this is a, I would say this is one of the second most obvious advantages of IoT. So understanding what exact quantities of supplies or the air quality in your home, which can provide more information that could not have been collected uh, easily, basic, right? So for example, if your milk is low in your grocery list, or your printer ink is low, all this can be kind of monitored and alerted. So it brings in a better monitoring. Then this all leads to a better quality of life, and it gives more comfort, more convenience, and you can manage your life better. So this all brings in a quality of life, especially IoT helping elders, people who live in remote parts. Uh, we'll be able to achieve a better quality of life for all of them. But all this comes with their own challenges. For example, one of the main important aspect is complexity, because all the devices are connected to the internet. Uh, you will have a lot of complex systems running each other, but these failures can kind of cause a lot of problems, and the problems will be like kind of skyrocket. For example, you get a notification, both you and your wife getting a notification of milk is low in your home. Both of you might end up purchasing it. It's in a small scale, but what if a device which is monitoring the electrical load on the grid saying wrong readings, right? So everyone will start to give a more output, produce more electricity, which might disturb the grid at the end of the day without any proper monitoring, right? Then it also put your privacy and security at risk, with all of this information not encrypted, available in your internet. People might easily tap into the personal information of the people, like what medication you use, what is your current financial situation. So this all brings in a lot of challenges to your individual privacy, security, or even the privacy of a corporate company, right? Then the safety. For example, what if somebody hacks into a system? where the water supplies are kind of properly not supplied to a city. What if somebody acts into a traffic signal, right? This can lead to a lot of problems. What if somebody gets into a nuclear reactor? For example, one of the incident is Stuxnet, which happened in Iran. So these all can brings in a lot of more safety related issues to the society. In terms of cyber wars, this can even pose a higher risk to the countries. What is optimal control, and how it is kind of going beyond the safety red lines. So, according to SCADA, when we define a control, it defines both optimal as well as the safety related aspects of it. So basically, what they're expecting is whenever we deploy any controls or any architecture, the control should include the optimalism as well as the safety aspects of it. So it should be a combined architecture. Why we need that is the major importance is basically IoT deployments becomes a playground for a lot of cyber intrusions. There are a lot of tampering activities which puts lives at risk, which puts countries at risk, which puts security aspects at risk. And also all these cyber intrusions can cause cascading effects because all these devices are interconnected. They are like it's a very complex architecture across the world. So these cascading effects will lead to some of the catastrophic events, which will put the entire security aspect of even a country or even multiple countries at a risk. There is a very less chance of accidental failures due to defective deployments, but the chances of that being happen is very less. The reason is before deployments, all this IoT system goes under very well quality inspections. So one of the major challenges for the IoT deployment is the safety, and how these particular optimal controls can cross the safety lines, right? So how we can kind of go beyond these problems is by doing an advanced deployment and also enabling the monitoring. So this helps us in achieving the safety to a certain extent, but not at a large scale. One example is Stuxnet. So Stuxnet is one of large-scale security safety incident in IoT where the Stuxnet virus got into the systems, and it can sit idle for a long time until unless it finds certain program which it can program to make defective outputs. So Stuxnet sits and waits for one particular version of Siemens PLC program. Then once it finds okay, this particular program is available, then it gives control to the machines, which can blow up even a nuclear reactor. So these aspects of optimal control can go beyond the safety red lines and cause some of the major problems to the countries. So that's one of the reason this optimal control should be always kind of controlled, and we always should have a monolithic architecture which combines both the control as well as the safety aspects for the particular IoT deployment. Even at the large scale, there should be a way for us to even evaluate all this. Presents a minimal TCB architecture. So, so, so there'll be a PLC cloud which will be available out of box, so that this can actually enable us from monitoring even before this particular control actions or any new code deployment to the PLC architecture can be controlled. So there is something called a shim layer implementation, which sits between the controllers and the monitors, the HMIs, to the actual actuators and sensors. So this shim layer also can run with the some sort of a mechanism where even before executing or transforming the commands to the actual actuators, it can actually make sure this particular command is not going beyond the safety red lines. So how this can happen is we have to have a separate deployments for the plant control from the safety monitoring, so that there is no intercommunication between them, or they are not deployed together. So and also the safety red lines enforcement should be based on a cloud-based controller with the analysis of what command is getting executed, and is it going beyond the safety red line or not. So that is what mentioned here. Mainly the PL's cloud agent is running in the shim layer, which takes the commands, which make sure, okay, this particular command is not giving any threat to this to the actual machines, and uh, uh, it's not going beyond the safety red lines. So how a threat model is coming into a picture. So what if somebody uploading a malicious code to PLCs, right? For example, somebody brings in a USB device and puts it into the machine, then directly modifying the PLC code, right? So this can happen in one system, but this particular piece of code should be evaluated with all the safety micro policies even before the deployment into the actual machine. And also when there is any findings happening in this particular piece of PLC code, the plant operator should also be notified. Then in case of any emergency situations, plant operators should be able to take any countermeasure activities. Either they should have any manual procedures to either take some action to either shut down the machine, or they should be able to have a mechanism to redeploy the previous version of the code or whatever. uh, but there is also a risk. What if this particular PL cloud itself is compromised by an insider, right, who have access directly? So there are people who have access to this particular PL cloud, who does maintain it. Of course, humans has to be involved. So in those cases, yes, PL cloud itself is not secured, but the chances are minimal in this case. So only less number of people can have access to it, and in case of any irregular activity, it can be logged. So who logs into the system, who did what. So those measures can minimize the risks to a greater extent. So the minimal TCP architecture proposes a shim layer where the PL Clouds agent is running, which can kind of suppress a lot of these problems even before these actuators are asked to do certain activities by the controllers or even by the HMIs. How basically this particular deployment helps ensuring this particular control actions or the optimal controls never cross the safety red lines. So there are certain micro aspects to it. For example, uh, the there should be a way to check the new code deployments to the PLC interfaces. So PLC has a certain port enabled where this particular port can be used to deploy new code or give control actions. So these ports should be monitored. The agent which is running to monitor these programs or monitor these control actions should understand, okay, there is a new command coming in. Then it has to take it and move it to a cloud-based emulator where this particular code behavior should be evaluated against a lot of security policies and security aspects. So all these micro policies should be enforced on that particular command or this particular piece of code, and they should be measured against the new safety red lines, whatever we define as a policy, safety policy or a security measure policy. So in case of any problems happening, the client agent should be notified with a sorry, the notification listener should be notified with what problems this particular piece of command or this particular piece of code can cause. So based on that, the plant operator or or even the automated process can take an action. Either it can reject this new code or new command or whatever. So it's more or less like kind of a testing, like a unit testing or even an integration testing for a large scale system, where this particular piece of code can be evaluated even before the deployment. Because in hardware world or in IoT world, where less software frameworks involved, having higher risk of getting into this kind of a problem. So this dynamic PLC source code should be able to uh, perform this transformation, make sure this emulator passing all this large scale security threat measurements, make sure the new code is, or the new control command is not going beyond certain limit. So 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 and also the PL cloud should share the same architecture as similar to the platform where this particular machine is running. It should be almost near perfect or near equal to how this particular system is in the field, uh, based on the operating system or based on whatever the software it runs. So there shouldn't be any lag in terms of reproducing the real world emulation in the PL cloud. And also, due to the bandwidth problems, the cloud agent should be able to communicate only the input controls to PLC, input controls to the PLC to the PL cloud. So the cloud can actually like take those control actions, then run the emulator, and in case of any hazardous findings, it can actually communicate to the notification listener, which can actually do a lot of other activities. Either it can take automatic actions, or it can even let the plant operator know about the risks. So in this entire operation, the communication mode is the important aspect. So this enables a very good solution for any of the optimal control not to go beyond certain safety red lines. And the PL cloud can resemble a near real world emulator, which can make sure even at a large scale this problem will never create any safety or security related issues. Well, how the PLC cloud is performing this entire security validation or verification is by emulation and monitoring and the notification. So the emulation takes care of making sure that the real world deployments are kind of simulated or emulated in a cloud based architecture, where the PLC commands are taken as an input from the cloud agent. Then those commands are executed in real time, making sure this particular command is not giving any safety or security threat by crash verifying against them, against the micro policies. Then then in case of any security incident, so the PLC cloud architecture should also keep a watch on what each of this command is going under different steps in terms of the emulation process. So in case of any security incident happens, then the monitoring or system should alert the plant operator through notification that this particular command is going to give troubles at the end of once it got deployed, or once the command is kind of actually given to the machine. So the plant operator should keep a watch on what commands goes in and what commands are raising the security flags by the PLC cloud. So in terms of monitoring the control actions, so uh, this increases the security of the system, and by increasing the security of the system, we have to deploy the access controls at every layer. That includes the monitoring system, so that people cannot even modify the alert thresholds. For example, even if a PLC cloud is giving a alert, but what if somebody modifies the alert threshold, so it might not raise an alert itself to the plant operator or to the notification listener. So that is where we should say we say it's an insider attack. So we should even make sure the monitoring systems are under monitored or under logging, so that people cannot tamper that system. So and also the control actions, whatever given to the machines, should be like kind of make sure any control actions which are safety of the which are related to the safety of the system should be alerted, and also should be evaluated. So and also all these actions should be cross verified against the redundant safety policies. On all these policies should make sure like they are implemented at micro level at every small step. For example, just by increasing or just by increasing the pressure of a turbine, there can be explosions. Just by giving a small control command, which can lead to a lot of safety issues. At micro level, these commands should be cross verified. Uh, and also IoT can be majorly used to mainly for monitoring rather than giving the control actions. That will reduce a lot of these problems. Or we have to make sure this control actions are monitored. These control actions are going under certain safety verifications. uh, and also whenever there are any automated control actions, there should be policies enforced. These control actions are monitored and goes under safety assessments. So there are prototypes which are developed in PLC cloud, where this kind of emulates a distributed PLC architecture of a real world, even in large scale, which performs better in terms of doing a security assessments. So yeah, we are near the end of the presentation. So thank you for watching. Thank you everyone.